Hello, my name is Will Aldridge, and I'm an application engineer with Parker Lord. I'm currently based on the West Coast, supporting our West Coast thermal management customers. Thanks for joining me for our second session of the Virtual Thermal Management Academy. So this course is TM201, and we're going to be covering the technical terms that you will encounter when evaluating, selecting, choosing, and using a thermal management product. So we'll go ahead and get started. So what we'll be covering today, we will be just covering general uncured and cured material property terminology. And specifically, we're going to be breaking it up into three categories. So thermal properties, mechanical properties, electrical properties. And last but not least, we'll be covering how to dispense thermal management materials as well as handle thermal management materials. Now, I also want to remind you guys that feel free to follow us on Twitter at Lord Corporation. And we'd love if you were able to follow along or tweet along using the hashtag thermalmanagement201 so you can share any thoughts and see anything that we share regarding this presentation. So Parker at a glance. We have more than 3,000 different product lines. We're located in 50 different countries. So we're able to really service customers all around the globe. We really are a global business with a local focus. Now, specifically, Parker Lord's manufacturing facilities domestically are located in Sagertown, Pennsylvania, as well as Indianapolis, Indiana. Globally, we also have some international ones. Other manufacturing facilities are in Brazil, Germany, Japan, and China. Now, our expertise. So we're heavily involved in the automotive market. So with traditional combustion engine vehicles, as well as the electric vehicle market, we are heavily involved there. But we certainly don't limit ourselves to that. We're involved in the energy industry, just general electronics. We also service the marine, industrial, aerospace and defense, and oil and gas industries. Our main products that we provide, as I mentioned, are thermal management materials. We also offer adhesives and coatings, sensing systems, electromechanical motion and vibration control systems, as well as traditional motion and vibration control systems. So we'll go ahead and jump into things here. So the first topic we're going to be covering is uncured material properties. So the first thing is going to be viscosity. So viscosity is one of those things that one of those properties, one of those things that we interact with on a day-to-day basis, even though we don't necessarily realize it. So the viscosity is the measurement of a material's resistance to flow at a given shear rate. Common units for viscosity are centipoise or Pascal seconds. And the viscosity of a material does vary with temperature. Now, when it comes to evaluating viscosity, a rheometer or a viscometer are used. So you can see that at the bottom of the screen there. Now, with relating it to, real world day-to-day things, you can see over on the right side of the table, there are some common liquids that we're all very familiar with. So water has a viscosity of 1 centipoise. Honey has a viscosity of 2,000 to 3,000 centipoise. Ketchup is around the 50,000 to 70,000 centipoise range. And then lard is very viscous. It's in the 1 to 2 million centipoise range. So that's just a nice frame of reference. So you can relate the viscosity of materials to the viscosity of general household items. Now moving on to the specific gravity. So the specific gravity is the dimensionless ratio relating the density of a material to the density of a reference material. Now, generally speaking, the reference material is water, but it doesn't necessarily have to always be. But for the products that we offer, it will be to water. Now, the specific gravity, when it is less than 1, that means that the material is less dense or lighter than the reference material. So if you refer to the image to the right there, you can see water is that green material about midway up the column. The ping pong ball that is on top of the column is less dense and lighter than water, so the specific gravity would be less than 1. Now, when the specific gravity is greater than 1, that means it is more dense and heavier than the reference material. So if you look at the bottom of that column, you'll see a bolt sitting down there in the honey. Both the bolt and the honey are more dense than the water. Now, knowing the material's specific gravity is definitely useful, even if you don't use the actual specific gravity itself. It's useful though, because you can extract the density of the material, and then from there you can extract the volume of the material that is being used, as well as the mass of the material. It's also worth noting that temperature can affect the specific gravity. Next, on to working time and pot life. These are two terms that are oftentimes used in place of each other, and really they're used to mean the same things, but at the end of the day, they do technically have different definitions, and really the difference is more semantics than anything. So the working time is the amount of time that is allowable between when a material is mixed and when the viscosity is too high that is no longer able to be easily applied or worked. So an example of this is if a material is rated for a working time of 30 minutes at room temperature, and once that material that has a 30-minute working time is applied, the substrate must be mated in less than 30 minutes, or if you wait longer, the material will no longer bond properly. Now switching over to pot life. The pot life is the amount of time that it takes for the material's viscosity to double. And an example of that is that if a material has an initial viscosity of 3,000 centipoise, once that viscosity reaches 60,000 centipoise, that is when the pot life is considered. So if it reaches 60,000 centipoise after 15 minutes, the pot life is 15 minutes. And both of these properties are very critical to know when selecting and using thermal management materials, so that you can ensure that it fits into your manufacturing process in a timely manner. Now moving on to time to handling strength and cure time. Time to handling strength is the amount of time that is required after mixing for an adhesive to reach sufficient strength to hold parts together without fixturing. Now, even though you can take the fixtures off and you don't have to have anything holding that bond or that joint or that seam in place, you still don't want to apply any sort of load to it. So this time to handling strength is also commonly referred to as the set time, the fixture time, or time to green strength. And this value is dependent upon temperature as well as the bond line thickness, the amount of material that is used. Next, going on to the cure time. The cure time is the amount of time that is needed after mixing for the adhesive to reach its final mechanical properties. So once you hit your final cure time, for example, if the final cure time is 24 hours, that's when you can apply a load. And that cure time will vary depending upon temperature as well as the cure schedule that is selected, so that relates to the temperature. Next, we'll transition on to the thermal properties. So thermal properties, one of the most common thermal properties that customers really care about when selecting a thermal management material is the thermal conductivity. The thermal conductivity is important because it really is the main factor that helps to reduce thermal strain, prevent performance loss, or even failure of components as a result of any heat that is generated. So the thermal conductivity is the ability of a material to conduct heat. Now, what affects that property? So the type of filler that is used when formulating the product greatly impacts the thermal conductivity. So that relates to the density, the specific heat capacity. Any air that is entrapped in the material when it is applied will impact the thermal conductivity, as well as the temperature of the application or of the test. So jumping on to what the units are typically for thermal conductivity, generally speaking, they're referenced in watts per meter Kelvin, but they can also be referenced in British thermal units per hour foot Fahrenheit. So the thermal resistance is another property. It is the measurement of a material's ability to resist the flow of heat. So it determines the effectiveness of a material's ability to draw heat away from a specific area. So for reference, materials that have a high thermal resistance, they don't transfer heat, while a material that has a low thermal resistance does transfer heat. And so the thermal resistance, it's worth noting that it is inversely proportional to the thermal conductivity. And so on the right here, you can see an image of our equipment that we use to test the thermal resistance. It is the thermal interface material tester, more affectionately known as the TIM tester. And the units for thermal resistance are Kelvin per watt. Now, the specific heat is the measurement of the amount of heat per unit mass that is needed to increase the temperature of a material 1 degree Celsius. Now, I know that's kind of a tough definition to digest. It's wordy, and it's not really easy to visualize. But a good example of this is with your dishwasher. So when you load up your dishwasher, you put all kinds of different things in there made of all different materials. For example, you'll have thin metal utensils, you'll have ceramic plates, ceramic bowls, metal bowls, plastic containers, whatever it may be. And once that dishwasher is done with the wash cycle, you've probably noticed that whenever you open the dishwasher and you go to take the material out, you see that, oh, hey, all the ceramic materials are completely dry. They're good to go. The bulky metal materials are also good to go. But the thin metal materials, they'll still be a little wet, and then the plastic materials are very wet. And you have to wipe them off with a rag, even though you just put them through a dry cycle. That is all because of the specific heat. And that is because the heat that is retained by ceramics is very high, so it's easy to evaporate that water off. Now, at the other end of the spectrum, there is the plastic material that is actually, the water forces the material to cool down so that it loses heat as a result of trying to evaporate that water. So that plastic material is super wet still at the end. And in the middle there is the metal. And so that's kind of the function of mass. And so sometimes it'll be more dry for heavy materials, and it will be less dry for thinner metals. So moving on to mechanical properties. One of the most common mechanical properties that we are asked about is the hardness. It's also known as the durometer. So when you hear us reference the durometer, it is a measurement of the hardness of a material such as rubber or plastic. Now, when it comes to polymers and elastomeric compounds, we typically use the Shore hardness scale. And for thermal management materials as a whole, and specifically Parker Lord's thermal management materials, everything pretty much falls on the Shore 00, Shore A, and Shore D scale. Now, Shore 00, as you can see in the plot below, Shore 00 is definitely on the soft side, and Shore A and Shore D are on the harder side. And so our silicone products generally fall in that Shore 00 range, and then the acrylic, epoxy, and urethane products fall on the Shore A to Shore D range. So next on to the glass transition temperature. The glass transition temperature is a property that is oftentimes overlooked when evaluating a thermal management material. The glass transition temperature is the temperature at which a material transitions from being firm and glassy per se to pliable and rubbery. So at this temperature, at the glass transition temperature, enough polymer chains start to move that the state of the material actually changes. So below the temperature, the material is rigid due to the lack of polymer mobility. And then above that temperature, the material is more flexible because there is some polymer movement. Now, this is critical because mechanical properties will change based on whether the temperature is above or below the glass transition temperature. Now, the one thing that really, the main thing that impacts the glass transition temperature, aside from the chemistry, is the cure schedule. So the higher temperature of the cure, the higher the glass transition temperature. Next on to the coefficient of thermal expansion. The coefficient of thermal expansion is the relationship between the fractional change in size and temperature change. So basically, it represents the extent a material expands when it is heated. So the larger the coefficient of thermal expansion for a given material, the more that it will expand per degree temperature increase. And units for this property are typically referenced in parts per million per degree Celsius. The linear cure shrinkage is the reduction in the size of a material during the manufacturing process. This reduction in size is generally caused by the reduction in free volume due to the cross-linking of the resin and the hardener, so the A side and the B side. It's also the result of the difference in the coefficient of thermal expansion between the thermal management material and the substrate. Now, using material with too large of a linear cure shrinkage value can result in defects and formations of gaps, and especially in applications where there's water or whatever, you're trying to use the thermal management material to double as a sealant, to protect water from getting in. You definitely don't want any gaps forming, because that water can definitely cause some damage to whatever is in that area if a gap forms. And so this is measured in the percentage change. And in the pictures below, you can see the areas where the thermal management material shrunk a little bit. So you can see that change in length. So next on to the tensile properties. So these properties are just very general. They're things that pretty much everyone is familiar with, but still definitely wanted to cover them. So first is the tensile strength. The tensile strength is the maximum stress material can withstand before fracture as a result of having forces applied to it, being stretched, being pulled. And you can see it where on the stress strain curve to the right, you can see where that fracture happens. That's where the tensile strength is measured to. The elongation is how far the material stretches or deforms in a linear fashion before fracture. The elastic modulus measures the material's overall resistance to deformation. Toughness is the ability of a material to absorb energy and plastically deform without fracture. Now, these four material properties, as I mentioned, they are pretty general, but they are greatly impacted as a result of the presence of any defects. So when that material is stressed, when a force is applied to it, that if there are any defects, it's just naturally a place where fractures can propagate from and the material can fail. Also, the loading environment, so the speed, the amount of loading there impacts it, as well as the amount of material that is applied or the specimen thickness. Next, on to the storage and loss modulus. Storage modulus is the measurement of the stiffness of a material and the ability of the material to store energy. It's the relationship between the stress and strain in the linear elastic region. And then moving on to the loss modulus. The loss modulus is the ability of a material to dissipate energy loss as heat. You may or may not have heard of loss modulus before, but the other name that could be more common is the viscous modulus. So you may be familiar with that term for this phrase. And it's the relationship between the out of phase component of the stress. Next, on to the latch shear strength. So the latch shear strength is just a common lab test that we use to evaluate the strength of our material when shear stress is applied to it. So you can see a picture of some of our lab tests to the right. So yeah, it's the shear strength of the adhesive for bonding material. Definitely a lot of things that impact this shear strength value, and it's the amount of material that is applied, so also known as the bond line thickness, the overlap area where the material is. Temperature has an impact on the latch shear strength, as well as the amount of time that is allowed for the material to cure. So if you try and test the latch shear strength or evaluate the latch shear strength of a material that isn't fully cured, it's going to be much lower than it is when it is fully cured. Environmental exposure, any sort of surface treatments, and just any intrinsic material properties also are driving factors in that latch shear strength. Next, on to the T-peel strength is a measurement of the peel separation strength of two substrates that have been bonded together. So T-peel, the reason why it is called T-peel, if you look to the right, the substrates when mated together look literally like a T. And so loads are applied in the X and Y direction, in the vertical directions, to pull the substrates apart, so it evaluates the strength of that bond there. And again, as I mentioned on the last slide, the amount of material applied, so bond line thickness, overlap area, temperature, and amount of time to cure, environmental exposure, surface treatment, and any intrinsic material properties also impact the T-peel separation strength. Now next, on to electrical properties. So the first one is the volume resistivity, which is a measurement of the electrical resistance of a unit cube of a material. So it represents a material's ability to limit leakage current between a component and its grounded heat sink. So you definitely don't want that. So and again, volume resistivity is oftentimes one of those properties that can be overlooked, but is definitely imperative when evaluating, selecting, and using a thermal management material. It can be significantly reduced by humidity and elevated temperature, and it's evaluated with the unit's ohm centimeters. Next, on to the dielectric strength. The dielectric strength is the critical AC or DC voltage of an electrical field at which the breakdown of a material takes place. So dielectric strength is often used interchangeably with breakdown voltage. So if you hear either one of those terms, it's the voltage at which the material breaks down. So what affects this property? The thickness or the amount of material that is applied. So it is a function of material thickness, the rate of applied voltage, electrical frequency, kind of the surrounding medium. So whether it's air, oil, whatever medium that it could be, temperature, moisture content, and again, intrinsic material properties. Next, on to the dielectric constant and dissipation factor. First, we'll talk about the dielectric constant. So it is a measurement of a material's ability to store electrical energy. So it's a ratio of the capacitance induced by two metallic plates with an insulator between them. When a material is required to be an insulator, a lower dielectric constant is ideal and really recommended. And when a material with a high capacitance is needed, a higher dielectric constant is preferred. Now transitioning on to the dissipation factor. The dissipation factor measures the infrequency to retain energy and act as an insulating material. It's the ratio of a material's capacitance to its resistance at a certain frequency. And as I mentioned before, with the dielectric constant, there is a preference on if you want the material to be more of an insulator. When recommending material, the lower the dissipation factor, the more effective and efficient the material is as an insulator, and the higher the dissipation factor, the more that energy is retained. And you can see below a sample of the specimen that are used in these tests, as well as the dielectric constant test unit. Now next, we'll move on to material dispensing and handling. What is used to dispense thermal management material? Yes, you can definitely apply it by hand, but a lot of times applications require much more accuracy and precision when applying the material. So that's when meter mix dispense equipment is used. The meter mix dispense equipment is used to transfer that material from a bulk container and then accurately meter the two components together in order to ensure that everything is on ratio. And then the MMD equipment dispenses through a static mixer to ensure the proper quantity as well as the proper amount of mixing is applied to the adhesive to really ensure that resin and hardener is mixed together. Some general high-level types of MMD equipment. So on the top, you can see gear pumps. At the bottom, you can see progressive cavity pump, which uses a rotor and stator. That rotor rotates, and as it rotates, it helps to force that material down along its fluid path. Also a rod displacement pump, and then a traditional piston pump setup. So that piston pump setup, there's a follower plate, and as material is needed, that follower plate is pressed down and the material flows up through basically the lines, and where then it can be mixed together and accurately metered after that. So moving on to the types, as I mentioned, but a little bit more focused on what types of products or systems they can be used with. So progressive cavity, they're great for gap fillers, thixotropic adhesives, as well as potting materials. And there's not really anything that we recommend not be used with progressive cavity pumps. Rod displacement MMD systems are great for gap fillers, thixotropic materials, and potting materials, so the same as the progressive cavity, but they're not ideal for lower viscosity products. Gear systems are very good for low viscosity encapsulants or adhesives, but the gear systems are not great for gap fillers or any products with glass beads or anything that is much higher viscosity, because it'll gunk up those gears and it won't be able to be transmitted properly. Next on to the piston pump style. MMD system, they're great for unfilled encapsulants and adhesives. Some systems, depending on the design, can dispense gap fillers as well as thixotropic materials. And then we do not recommend these for highly engineered systems that have, glass beads or, higher viscosity. So we recommend avoiding those with the piston pumps. And then the vacuum potting is another system that can be used, definitely recommended for moisture sensitive systems and any low viscosity products, but it's not great for thixotropic materials or higher viscosity products. And so tying everything together there with the MMD system, you can get different fluid bodies, fittings, seals, different components of that MMD system can be made of different things. And based on the type of chemistry that is being used, you'll need different type of materials for the fluid bodies, fittings, seals, packings, and hoses. So I won't dive too deep into this. You guys can take a screenshot if you'd like, and you guys can always reach out to any of the application engineers or any of us to provide any recommendations when it comes to selecting MMD equipment or choosing the individual components of the MMD system. So last but certainly not least is the data sheets. So the data sheets are the home of all of this information that we covered. So all these mechanical, electrical, and thermal properties for any product, whether it is from Parker Lord or from any other thermal management company, all those properties are going to be on there. And so it's a great reference to compare and contrast the different properties of different products. So the data sheets, the technical data sheets are going to be the home of all of those. And then when it comes to, more health and safety, handling, protective measures, those things can be found on the safety data sheet. And so there's a safety data sheet for both the resin and the hardener of all of our thermal management materials. So that's another great thing to consider when selecting thermal management materials. And so specifically for Parker Lord, our TDSs and SDSs can be found on lord.com on the page for the specific material. So key takeaways. First and foremost, uncured properties are critical to understanding how a material will fit into your manufacturing process. Definitely have to have a good understanding of how the property is going to react prior to it curing so it can fit into your process. Next, thermal properties determine a material's reaction to heat. Mechanical properties represent how a material will act when forces are applied. Electrical properties show the way a material responds to electrical currents. And so those may seem obvious, but definitely wanted to highlight those there. And at the end of the day, when it comes to selecting dispense equipment, MMD equipment, there are a ton of different options available, similarly to the way that there are a ton of different materials that can be used to fit your need. So the material properties can greatly impact what you choose. So definitely recommend comparing and contrasting so you can make a wise decision and not regret it down the road. With that being said, I'd like to thank you guys all for attending. Everyone, this was a lot of fun. Looking forward to some of your questions here in a second. But I also wanted to highlight that if you really enjoyed this or you enjoyed the first presentation, we invite you back on February 18th for our overview of silicone properties. And then after that, we'll also be highlighting epoxy properties on February 25th. And on March 4th, we'll be highlighting urethane and acrylic properties. So if you're interested in attending any of those virtual academy sessions, feel free to scan the QR code up on the upper right-hand corner of the slide and definitely register so we can see you back. But with that being said, I'd like to open the floor for questions. Thanks for joining.